Welcome to EFSA's e-learning on uncertainty analysis for chemical risk assessments. I'm Andy Hart, and this is the second of 3 presentations in the course. This course presents practical options for applying EFSA's guidance on uncertainty analysis in chemical risk assessments. There are 3 presentations: Introduction and Identifying Uncertainties, Basic Options for Assessing Uncertainty, and Refined Options, and the key principle throughout is to tailor the uncertainty analysis to what is necessary and useful for each assessment. In the first presentation, I introduced the concepts of standardized procedures in assessments of regulated chemicals and case-specific assessments, which are generally needed for non-regulated chemicals and contaminants. I explained the need to systematically identify sources of uncertainty in all assessments, and that when no non-standard uncertainties are found when using the standardized procedure, no further uncertainty analysis is required. In all other assessments, when non-standard uncertainties are present, and in case-specific assessments, further steps are needed to assess the impact of the uncertainties on the conclusion of the assessment. The final goal of these further steps is to assess overall uncertainty, the combined impact of all the identified uncertainties on the conclusion of the risk assessment. The options for assessing overall uncertainty are basic uncertainty analysis, where you assess the combined impact of all the identified uncertainties in a single step by expert judgment, and refined uncertainty analysis, where you assess some sources of uncertainty separately before assessing overall uncertainty. Again, the key principle is to tailor the uncertainty analysis to what is needed. So use the basic option when it's sufficient and keep the refined options for when they are needed. This presentation describes how to apply the basic option in chemical risk assessment, while the final presentation goes on to refined options. One or other of these options is required in all chemical risk assessments, except when using standardized procedures and no non-standard uncertainties are present. The starting point for both options is the list of uncertainties identified by the assessors. You'll remember I showed 3 examples of such lists in the first presentation. One from EFSA's Contam panel, one from the FAF panel, and one from the SEP panel. So, how did these opinions assess overall uncertainty? They all assessed it qualitatively using expert judgment. The Contam panel concluded, given the uncertainties, the risk assessment of human and animal exposure to the sum of T2 and HT2 toxins is more likely to overestimate than underestimate the risk. The FAF panel concluded, overall, on the basis of all currently available evidence, along with all the uncertainties, the panel concluded that E171 can no longer be considered as safe when used as a food additive. And the SEP panel concluded that the conservative approach applied to the exposure estimate for food enzyme TOS is likely to have led to a considerable overestimation of the exposure. These are qualitative expressions of overall uncertainty, but EFSA's uncertainty guidance recommends assessing overall uncertainty quantitatively using probability. Let's look at the reasons for that. Qualitative expressions of uncertainty or confidence are ambiguous and interpreted differently by different people. A wide variety of words is used to express uncertainty in everyday language, but almost all of them are ambiguous. Let's look at our third example. The conservative approach is likely to have led to a considerable overestimation of the exposure. Here, the word likely expresses uncertainty about whether there is considerable overestimation or not. If you ask a group of people what probability they associate with the word likely, you will get responses ranging from under 50% to over 90%. In the study shown here, it was a group of plant health risk assessors, but you'll get a similar range of interpretation with any group of people. This has two serious implications for risk assessment. First, it means that when doing an assessment, a group of experts may agree a conclusion is likely when in reality they have quite different opinions. Expressing their judgments using probability reveals the differences so that they can discuss them and arrive at a better consensus. Second, if the experts report a conclusion as likely, the risk manager's interpretation of this may differ markedly from what the experts intended, which could have an impact on risk management decisions. So, EFSA's uncertainty guidance recommends quantifying overall uncertainty using probability because it has defined meaning, which is more transparent and can be interpreted consistently by assessors and risk managers, as well as stakeholders and consumers. So what is the defined meaning of probability? The EFSA uncertainty guidance expresses probability as a percentage between 0 and 100%, where 100% means the conclusion is certain to be correct, and 0% means the conclusion is certainly not correct. The conclusion could be a statement, for example, that exposure is below the tolerable daily intake, or it could be a range for a quantitative estimate, for example, the exposure of a high consumer. Intermediate probabilities are defined by reference to well-understood standards. For example, if we say that a conclusion has a probability of 50%, we mean it is as likely as getting heads when tossing a coin. We judge that the conclusion is equally likely to be correct or incorrect. More probabilities, from 1 chance in 6 to 5 chances in 6, can be defined by comparison to rolling a dice. And any probability can be defined by comparison to taking coloured balls from a jar or a bag. For example, 90% probability means 9 chances out of 10, as likely as drawing a red ball from a jar containing 9 red balls and 1 black one. So, how can we quantify uncertainty using probability? Of course, it's good to calculate probabilities from data when suitable data are available. However, overall uncertainty must always be assessed by expert judgment because there are always some uncertainties that cannot be quantified from data. For example, statistical analysis can give you a confidence interval for a mean concentration or a benchmark dose, but this only quantifies those uncertainties that cause variation in the data, such as sampling variation. It does not take account of uncertainties about the reliability of the data, their relevance to your assessment, or the assumptions involved in the statistical analysis. Assessing those always requires expert judgment. Just describing those additional uncertainties is not sufficient because it leaves the risk manager to assess their impact on the conclusion for themselves. And assessing their impact qualitatively does not avoid expert judgment, it just makes it ambiguous. Of course, expert judgments must be based on evidence and reasoning, which must be documented, and expert judgments are subjective and affected by psychological biases. So for these reasons, EFSA guidance provides structured methods for probability judgments to ensure they are based on evidence and reasoning and guard against bias. Formal methods are described in EFSA's guidance on expert knowledge elicitation, or EKE, while simpler, less formal methods are described in Annex B8 of the Scientific Opinion on Principles and Methods for Uncertainty Analysis. These documents describe the methods in general terms to cover all areas of EFSA's work. So in this presentation and the next one, I describe practical ways to apply them in basic and refined uncertainty analysis for chemical risk assessment. I will illustrate the basic approach to assessing overall uncertainty using the Contam panel's assessment of T2 and HT2 toxins, for which we saw a list of uncertainties earlier. This is a case-specific assessment with some standardized elements. For example, the tolerable daily intake, or TDI, is based on a benchmark dose, the BMD-L05, for the critical effect, and the default uncertainty factor of 100. And the exposure estimate for a high consumer is based on the 95th percentile from EFSA's comprehensive database of dietary survey data. I want to emphasize that although the example here is a contaminant, the approach to assessing overall uncertainty is general and equally applicable to regulated chemicals when non-standard uncertainties are present. First, we need to recall the key points of the Contam panel's assessment. The hazard assessment resulted in a TDI of 100 nanograms per kilogram body weight per day. The exposure assessment was carried out for different EU countries, and the highest estimates for the 95th percentile consumer were 65 nanograms per kilogram body weight per day, assuming non-detects are equal to 0, and 91, assuming non-detects are equal to the LOD, the limit of detection. The panel's conclusion on risk was estimates of chronic human dietary exposure are below the TDI for populations of all age groups and thus not a health concern. I've represented that here. The TDI is 100 nanograms per kilogram body weight per day. The highest exposure estimate was 65 nanograms per kilogram body weight per day, assuming non-detects are 0, and 91, assuming non-detects are equal to the limit of detection. So the panel concluded that there was no health concern. When reaching this conclusion, the panel took account of the uncertainties they had identified. Some of these uncertainties affect the exposure assessment, while others affect the hazard assessment, and the plus and minus symbols indicate that the panel considered most of the uncertainties could result in either overestimation or underestimation of risk. This implies that if the uncertainties could be taken into account, the TDI might become either higher or lower. The exposure estimates might become either higher or lower, and therefore the risk could be either higher or lower. This was recognized by the Contam panel in their qualitative assessment of overall uncertainty. Given the uncertainties, the risk assessment is more likely to over than underestimate the risk. If the TDI was lower and the exposure was higher, then it is possible that the highest 95th percentile exposure could exceed the TDI. But the panel's conclusion that there is not a health concern implies that they were sufficiently certain that exposure is below the TDI. In other words, they judged that the probability of exposure being below the TDI is sufficiently high. This is the point where applying the uncertainty guidance requires an extra step, quantifying the overall impact of the uncertainties on the conclusion of the assessment using probability. A simple way to do this is to use the approximate probability scale which the uncertainty guidance document recommends for harmonized use in EFSA. Specifically, the experts who are conducting the assessment are asked to assess the probability of exposure being below the TDI and express their judgment about this by choosing one or more ranges from the scale. The reason for doing this is that it makes that critical final judgment explicit, unambiguous, and transparent. It does not imply a need for any extra analysis or calculations. It just requires using probability to express the same expert judgment that was already made. This can be done by semi-formal expert elicitation in 4 simple steps. Agree a well-defined question, decide which experts will participate, have the experts work separately to make individual judgments, and then hold a facilitated discussion leading to a consensus judgment. I'll explain each step in turn. Step 1 is to agree a well-defined question for the experts to assess. The guidance on uncertainty explains that a well-defined question specifies an experiment, study or procedure that could be done, at least in principle, and would determine the answer to the question with certainty. The purpose of this is to ensure that all the experts interpret the question in the same way. In this case, what we'd like to know is the expert's probability that the true highest 95th percentile exposure is below the true TDI. However, this isn't really a well-defined question, because although there is in principle a true or real highest exposure that could in principle be measured, the TDI is not directly measurable. It is the result of a procedure where a set of toxicity studies is conducted and the lowest BMDL or no AEL for a relevant and adverse effect is combined with appropriate uncertainty factors. So a more appropriate way of framing the question might be something like this. If all the identified sources of uncertainty were fully resolved, for example, by obtaining perfect information and were addressed in the assessment, what is your probability that the highest 95th percentile exposure would be below the TDI, where perfect information could refer to precise measurements of actual exposure and a perfect set of toxicity studies. The important thing is that the experts involved in the assessment frame the question in such a way that they are confident they all interpret it in the same way. Step 2 is to decide which experts will participate and provide basic training. There should be multiple experts covering the range of expertise required for the assessment. If the assessment's being performed by an EFSA working group, a good default would be for all members of the working group to participate. The experts should receive basic training in making probability judgments. This is available within EFSA. Training should include an introduction to probability like the one earlier in this presentation and an explanation of how to use the approximate probability scale, which we will come to shortly. It is also helpful to practice making a probability judgment for an example question before you do it in a real assessment. Step 3 is where the experts review the evidence and uncertainties and make individual judgments. The evidence and uncertainties should be available in the draft assessment or opinion, and the experts should work separately to make individual judgments on the question. It's efficient if the experts can do this between meetings, after being trained, and before the meeting where their judgments will be discussed. So, how can experts use the approximate probability scale to make judgments on the defined question? Each expert selects one or more probability ranges from the scale to express their judgment of how likely it is that the highest 95th percentile exposure would be below the TDI if all the uncertainties were resolved. This is not guessing. It should be a careful, reasoned judgment, using the assessor's expertise and taking account of the evidence and the uncertainties that have been identified. For example, if they think that the assessment is very conservative and are very confident that the true 95th percentile exposure would be lower than the estimates and that the TDI from a perfect set of toxicity studies would be higher, then they might be very confident that the exposure would be below the TDI, in which case they might choose a probability range near the top of the scale. For example, if they think that there is at least a 9 out of 10 chance that exposure will be below the TDI, they might select the range from 90 to 95%. On the other hand, if the expert thinks that exposure and hazard are both very uncertain and might be either a lot lower or a lot higher, then they would be less confident that exposure is below the TDI and give a lower probability, perhaps somewhere in the middle of the scale. It is not necessary to restrict yourself to the ranges shown in the scale if a different range expresses your judgment better. For example, if the expert judges their probability to be between 50 and 75%, they should say so. Step 4 is facilitated discussion leading to consensus judgment. The process here is to share and discuss the individual judgments of the experts and develop and agree on a consensus judgment of the group. This should be facilitated by a person who is not contributing to the judgments themselves. For an EFSA working group, the facilitator might be the chair if they are not making judgments themselves, or an EFSA scientific officer supporting the working group, or you can request a specialised facilitator from EFSA's Assessment Methodology Unit, which I would recommend, at least for the first time you do this. This process of making individual judgments separately and then sharing them is important. It ensures all the experts contribute and that different interpretations of the evidence and uncertainty are taken into account. It might take half a day the first time you do this, but it should get a lot easier and quicker with experience. It is important to be clear what type of consensus is needed. It is not required that the experts' personal judgments all converge to the same answer. A compromise where some experts defer to others is not a consensus and would be inappropriate. Arbitrary averaging of the individual judgments is also inappropriate unless the experts explicitly agree that the average is their consensus. So what do we mean by consensus? We mean the type of consensus that is sought by the Sheffield method in EFSA's guidance on expert elicitation. Specifically, the group is asked to consider what a rational, impartial observer, or RIO, would judge, having seen the evidence, the uncertainties, and the individual judgments, and heard the discussion. One way to make the RIO concept more concrete is to think of it as what it would be rational for the risk manager to think, based on the evidence and the combined advice of the experts. This is appropriate because EFSA's assessments are intended to inform risk managers. If the experts find it difficult to agree on a consensus probability or range, they should choose a wider range that reflects the extent to which their individual judgments still diverge after discussion. Having completed the assessment of overall uncertainty, we need to consider how to report the outcome. The outcome is the assessor's consensus probability range for the exposure being below the TDI. One option is to incorporate this into the conclusion of the assessment. For example, the panel is 90 to 95% certain that exposure is below the TDI. Expressing probability as percent certainty of the more probable outcome is a suggestion from EFSA's guidance on communication of uncertainty. This has the advantage of being transparent about how certain EFSA is of the conclusion. However, the uncertainty guidance recognises that in some areas of EFSA's work, especially regulatory assessments, legislation or risk managers currently require firm conclusions without probabilities. Nevertheless, it is still beneficial to use probabilities while conducting the assessment, even if they are not included when reporting the conclusions. This can be accommodated by defining what level of certainty, i.e. probability, is required for each type of conclusion. For example, if your assessments normally report conclusions in terms of health concern, definitions could be established for the level of probability that would justify reporting no health concern, and at the other end of the scale, the level of probability that would justify reporting a health concern, with intermediate probabilities being reported as inconclusive. It would not be appropriate for me to suggest what these probability thresholds might be, because they involve judgments about what level of certainty is acceptable, so they should be agreed with risk managers and published if possible for transparency. Once the thresholds are defined, the assessors can quantify uncertainty in terms of probability when conducting the assessment, but translate this into the appropriate verbal conclusion for reporting. This enables you to meet the requirements of EFSA's uncertainty guidance without changing the way that you report your conclusions. Even though you might reach the same conclusion as you would have done from a qualitative assessment, using probability to assess overall uncertainty is still beneficial. Because probability has defined meaning, the assessors will have a clearer understanding of each other's judgments about the conclusion, enabling a better discussion and a better reasoned consensus. And risk managers will have a clearer understanding of how certain the assessors are of the conclusion, providing a better basis for decision making. In summary, this presentation focused on the simplest option for quantifying the overall impact of the identified uncertainties, which is to assess them collectively in one step using expert judgment, a basic uncertainty analysis. I explained why EFSA's guidance recommends using probability for quantifying overall uncertainty, and I introduced EFSA's approximate probability scale. I described 4 steps for using the scale to elicit probability judgments from the experts conducting the assessment, and I ended by explaining how defining probability thresholds can enable you to continue reporting your conclusions in your normal way. I used an example from EFSA's contam panel to illustrate these approaches, but they are equally applicable to chemical risk assessments in other areas. In the final presentation, we will explore refined options for uncertainty analysis, where some uncertainties are assessed separately before quantifying overall uncertainty. For example, when it's helpful to assess exposure and hazard uncertainties separately first, and then combine them.